Hi everyone, today we are going to be learning and reviewing how to simplify radical expressions. The review part will be simplifying square root expressions using the product property, but then we're also going to learn to simplify square root expressions that have a negative radicand or number inside of the radical using an imaginary number called I. So first let's just review some vocabulary. We have the radical symbol, and we are going to have a number above the radical symbol here that's called the index. With square roots, there is a 2 there, but we are going to infer that whenever there is a radical without an index listed, that it is a 2. Later in this year, you'll see other indexes, numbers like a cube root or a root with an index of 3, a fourth root, a fifth root, and so on. The other important piece of information is that the information inside of the radical is called the radicand. So in all of these problems down below in this next section, all of these numbers are radicands inside of square root functions. Okay, so let's just review some perfect numbers. So first, when you have a square root, we are going to sometimes in our directions be asked to find the principal square root. And that just means assume that the square root is positive. So we're only going to give positive answers when we're asked for the principal square root. So the square root of 4 is 2 times 2, so that's a pair of 2's. The square root of 4 is 2. The square root of 9 is 3, the square root of 4 is 16 is 4, the square root of 25 is 5, the square root of 36 is 6, the square root of 49 is 7, the square root of 64 is 8, the square root of 81 is 9, the square root of 100 is 10, the square root of 121 is 11, the square root of 144 is 12. So now there are 3 more that I would like for you to know this year because we're going to come across them often. The square root of 169 is 13, and the square root of 196 is 14. 225, the square root of it is 15. Now, to help you remember these last 2 in particular, because these might be the ones that you're not as familiar with, notice that the 96 and the 69, those 2 numbers are swapped around. So the smaller number, the 169, is the 13, and then right after that one, 96, the numbers flip places, that's the square root. That gives us the 14. So hopefully that might give you a little bit of a reminder as to which one is which and how to remember them both. You are expected this year to have all of these square roots memorized. They are going to be absolutely essential that you can recall from memory. You should not need a calculator to simplify these radicals and radicals that use them. So let's get into the actual simplifying part when we don't have a perfect number like these. So our steps are going to be to make a list of perfect squares to keep in sight. We have that on the top of your page right now. And then to factor using the largest perfect square. And then we'll simplify so that the radicand can't factor anymore with any perfect squares. So I'm going to show you 2 methods to do this. I'm going to show you the alternative first because I think that's probably what you have done in the past, and then I'll show you a much better method using these perfect numbers. Okay, so in the past when you've simplified square roots, you've probably drawn a tree, right? So if we're trying to simplify the square root of 72, you may think immediately that 72 is 9 times 8, and then break 9 down into 3 times 3, so there are our smallest numbers, and then 8 is 2 times 4, there's a 2, and then that 4 gets broken down into 2 times 2. So then we can rewrite our radical as 3 times 3 times 2 times 2 times 2, where we take both of these 3's and write them down, and we take all 3 of these 2's and write them down inside of the radical. And then because this is a square root, we're looking for pairs. So we have a pair of 3's, so they come outside of the radical. We have a pair of 2's, and this is all multiplication, notice, so that comes outside of the radical. And then we have this 2 that doesn't have a pair, so he's going to stay inside of the radical. And then we just need to simplify our multiplication. 3 times 2 is 6, and we have 6 square roots of 2 as our final answer. So that's probably similar to what you've done in the past. I want to offer an alternative that will be a bit less work a lot of times. So if we have a radicand like 72, we can start listing numbers to multiply together to get to 72. And when we do this, we want to go in order. So I'm going to start with 1 times 72, and then I'm going to look at, is there anything that I can multiply 2 by, then 3 by, and so on. 72 divided by 2 is 36, so that works out nicely. 72 divided by 3 is 24, so 3 times 24. And now I could keep going, but I'm actually going to stop right here because when I did 2 times 36, I see a perfect number from that list that a moment ago I asked you to memorize. I see the square root of 36 is something that's easy to take the square root of. So I'm going to rewrite the square root of 72 as the square root of 36 times 2. Using that set of factors. And then the square root of 36 and the square root of 2, we can think about those as separate radicals because that is our multiplication property with radicals. We'll get into that a little bit more later. And then the square root of 36 is 6. So we have 6, the square root of 2 does not simplify, and it gets me to that exact same answer, but without all of the having to like group things together and make sure I didn't miss anything and all of that. It's also in simplest form, so I don't have to continue simplifying the radical at all. So let's try a couple of practice problems before we get into negative numbers. This next one says the square root of 27. So I'm going to write 27 and I'm going to make a list of numbers that multiply together to get to 27, and I'm going to stop when I find a perfect number. So I've got 1 times 27. 2 doesn't go into 27 because 27 is odd. 3 times 9 is 27, and I'm going to stop right there because I have a nice big perfect number. I have a 9, so I'm going to write this as the square root of 9 times 3. The square root of 9 is 3, and the square root of 3 just stays the square root of 3. So that 9 I took the square root of, and I'm done with that. Let's look at 32. If I make my list of factors, I've got 1 times 32. 2 goes into 32 16 times, and I'm going to stop right there again because 16 is a perfect number. I can rewrite the square root of 32 as the square root of 16 times 2. The square root of 16 is 4, and the square root of 2 stays as it is because it doesn't have a pair to come out, and that's my final answer, 4 times the square root of 2. All right, so now let's try some that have negative numbers in them. With these, when we have to solve quadratics and there aren't any real solutions, we can use what's called an imaginary number. It's the number I to get rid of that negative, or to find a solution that incorporates that lack of real solutions. So mathematicians have defined I to equal the square root of -1. And this is a very important fact for you to have memorized as part of the perfect numbers and radicals that you need to know. So if I have a square root of some negative number, I can think about that as the square root of -1 times that number. And then the square root of -1 is going to be I, so an I is going to come out of that radical. So let's look at an example. First, I'm going to rewrite the square root of -6 as a square root of -1 times 6. Then I'm going to use my method over here to think about things that multiply together to get 6. I have 1 times 6, and I have 2 times 3. None of those are perfect numbers, so nothing's going to come out, and there aren't any other numbers that multiply together, or any whole numbers that multiply together. So we're going to leave the 6 inside, but the square root of -1, I'm going to break this up just so it's easy to see. The square root of -1 is I, and then that's being multiplied with that radical that won't simplify, the square root of 6. So our final answer for this one is I square roots of 6. let's look at another one. We have the square root of negative 81, so that's the square root of negative 1 times 81. I'm going to break that into 2 again just to see all of the steps here for a moment. So I've got the square root of negative 1 times the square root of 81. The square root of negative 1, using our definition of I, is I, and the square root of 81 is 9. Now we are going to write these in order like I is a variable. So if you have a number like 9, a whole number, you're going to write the 9 and then the I, the same way we would write 9x instead of xi. The one exception to that, you'll notice in this previous problem, is that I left the I out front of the radical. If you have a radical, the I is going to be on the outside. Do not put the I like this, because without this little end tail here, it looks like the I might be inside of the radical. So it's best practice to just always write the I out in front. All right, let's look at one more that's going to have a couple of things going on in it. So in this one, we have the square root of negative 50, so that's negative 1 times 50. For 50, I'm going to write my list of numbers, 1 times 50, 2 times 25, and I'm going to stop right there because 25 is a perfect number. So I'm going to rewrite this as the square root of negative 1 times 25 times 2. Now, you can break this up into separate pieces as you want. I'm going to skip that step just because I'm hoping that you're seeing the pattern now. The square root of negative 1 is I, so the I comes outside. The square root of 25 is 5, so the 5 comes outside. And the square root of 2 does not simplify, so I'm going to leave that square root with the 2 inside. Now, in terms of order here, I want my 5 in the front. Then I'm going to have my not a variable, but like a variable I, and then my radical is going to come at the end. And that order will be the order that you always use. It will always be the whole number, then the imaginary number, and then the real number. So 5i square roots of 2. And this is the same as saying 5 times I times the square root of 2. Okay, so with that, now you can simplify square root expressions using the product property. You can use the tree if you'd like, but the product property is going to save you several steps and possibly some mistakes. And you can also simplify square root expressions when there's a negative radicand by using that imaginary number I. Go ahead and try the practice problems for us to talk about in class.